Hi everyone. In this video, I'm just going to finish off 10.4 and then we're going to have a look at section 10.5. In the previous lecture, we touched on the first two bullet points, and in this video, I just want to do a quick recap on the second one, calculating the probability of a type 2 error and a sample size, and then how you're going to calculate a large sample confidence interval. So this is one of the slides that we looked at already in class. So remember, when you're testing for equal proportions, then this is your standard error for p hat 1 minus p hat 2. So remember, p is the pooled proportion. And so remember, it's just coming from this. We're assuming p1 and p2 are equal, and we just call it p. Q1 and Q2 are also assumed to be equal, so it's just called Q. So you end up with this standard error when you have assumed P1 equals P2. But remember, for type 2 error, you want to find the probability that you do not reject H0 given that HA is true. So if HA is true, that means P1 and P2 are going to be some different values. And that means now your standard error is just going to be this formula again, because you're no longer assuming equality. And then based on this, now you can calculate your type 2 error. And in this case, rather your probability of a type 2 error. So you'll be given a P1 and a P2, so that's why it's written this way. And these are supposedly the true values. So these formulas are what you'll be given in your semester test and exam. You need to be able to apply as well as derive them. These are given on page 522. So let's have a look at the proof. So just bear in mind that if HA is true, this is going to be our standard error. So for starters, let's look at the upper tailed test. You should be able to do the other two. So we just start off with the definition, so you always start there. And then remember, you're going to reject for large values when this is your alternative. So therefore, you will not reject for small values of your test statistic. In other words, Z less than Z alpha. And we're still assuming HA is true. So therefore, now if you put your test statistic in there, remember it's p hat 1 minus p hat 2 divided by this. So all we did to get this step was multiply both sides to get that part. Okay. Now we're assuming HA is true, so we're going to standardize assuming HA is true. So we'll subtract P1 minus P2 as given, and then we'll divide by sigma. And this sigma is exactly this equation here, or the textbook equation 10.6. So you'll find that if you go back to the table where they give you all the beta type 2 errors, this is the probability that you're going to be looking for. So this proof is almost done. And then remember, p hat is this weighted average of p hat 1 and p hat 2. But we've been given a p1 and a p2, so it follows that these two things are approximately equal. So instead of calling this thing p hat anymore, we're just going to call it p bar. And the only difference is just that instead of using the hats on P1 and P2, you'll just use the ones they've given you, and you'll use a P bar. Now, if you want to calculate a sample size, on page 523, they give you this formula. This is a formula that you need if you're going to find a sample size given some beta, alpha, and this is for any lower or upper tail test. If you want to do the sample size for a two-sided test, then you need to replace alpha over 2 in place of all the alphas for a two-tailed test. Sorry. The self-study, have a look at 10.12, so you'll see how they apply this. And then for your own practice, you should do exercise 49B and see if you get the same answer. On page 524, they give you the confidence interval, which you need to be able to derive. So you're going to follow the same procedure as in chapter 8. This is your pivotal quantity. Remember, we're no longer assuming equal variances. So instead of having P1 minus P2 equals 0, we're going to put it right back in as it was in the original case. And here you have P1, Q1. Remember, we're no longer assuming equality. So you're not going to have that global P and Q as we had earlier. You'll have specifically the P1 and the Q1 and P2 and Q2. So if you follow this procedure as usual, you want to find 101 minus confidence interval for P1 minus P2. So you can just ignore that small error there. But here your target is to find this. What can you put there and there such that the probability of this thing being between those two values is 1 minus alpha? So you're going to start from here with that value, and then you're just going to manipulate this test statistic, or rather pivotal quantity, so that you end up with this thing, only this part in the middle. And then remember, we don't actually know what P1 and Q1 are, so you'll just put hats on those to indicate that we're actually going to use the estimates for the sample. So the final result that you should get is P hat 1 minus P hat 2. And notice the hats are also there as well. So just make sure you can derive this result from here. Example 10.3 is available for self-study, so they just calculate a confidence interval, and you can do exercise 51 as practice. So now we are done with this. Let's have a look at 10.5. In section 10.5, we will be looking at inferences about two population variances. Let's start off with the hypothesis test. This is going to be the hypothesis test that you're going to look at. It's always going to be for equal variances. So you don't have to worry about this difference being anything. We don't even talk about the difference. We're going to just test whether it's equal versus any of these three different cases. Note well that this null hypothesis is equivalent to this one. So in other words, that the standard deviations are equal. So the way that you test this hypothesis is exactly the same procedure for testing this one, because these two things are equivalent. If you go back to chapter 6, this theorem is given. They tell you that if you have two samples, x1 up to xm and y1 up to yn, such that both of them actually follow normal distributions and they're independent of each other, then you have an f distribution if you calculate this function here, and it's going to have m minus 1 and n minus 1 degrees of freedom. So this is going to be the basis of our test statistic. We're going to build it from here. So if I just start off with the result that they've given us, you can rewrite this like this. So it's s1 squared over s2 squared times sigma 2 squared over sigma 1 squared. Now remember, under the null hypothesis, we assume equality of variances. So another way of expressing this null is saying that sigma 1 squared over sigma 2 squared is equal to 1, or even the reciprocal is equal to 1. So all of these hypotheses in the brackets are equivalent to that one. So if we know that under the null hypothesis this thing is equal to 1, then if we now apply it here, then we're going to end up with this as our test statistic. And naturally, it's going to follow that since this is our null, then then this sigma 1 squared equals sigma 2 squared is going to be rejected if the ratio differs too much from 1. So it's just looking at this interpretation of the same null hypothesis. So let's have a look at the summary. I'm just going to do it for you quickly as we've done in class, and you can just add it on to your table. So in summary, Our target is going to be sigma 1 squared and sigma 2 squared, or the standard deviation, sigma 1 and sigma 2. Our null hypothesis is always going to be sigma squared 1 equal to sigma squared 2, or similarly sigma 1 equals sigma 2. Just depends on the question. And then it doesn't matter which case, even though these might appear a little bit different, the test is exactly the same. So we're assuming independence for both populations, and we assume one has a sample size m, the other one has a sample size n. Now, regardless of which one you're testing, your test statistic is going to be f equal to s1 squared over s2 squared. So just make sure that if you're given an s1 squared, just an s1, so in other words, a standard deviation, then just make sure you square it before you use that formula. And this thing has an F distribution with m minus 1 degrees of freedom and n minus 1 degrees of freedom. And then in terms of just additional notes, there's not a lot that you have to know for this. You need to be able to find p-values for this, and I'll show you how to do that in the upcoming slides. And you also need to be able to derive the confidence interval. On page 528, they give you this table where they summarize the different possible hypotheses that you might want to test. So remember, this is exactly equal to that null hypothesis. The test statistic is the same in both of these cases. And then the alternatives could be any one of these. It could be an upper, lower, or two-sided test. And then these are your rejection regions. So it doesn't matter if it's that one or that one. Everything else remains the same. Okay? So let's start off with this top one here. Remember, your upper tail area should be alpha, so it's going to be m minus 1, n minus 1 degrees of freedom. And then in the textbook, they give alpha, which is exactly the same as this one, but that's a mistake. I believe it should be 1 minus alpha, because the area to the left should be alpha. So this is the case that they have there. However, I guess it wasn't really a big deal for them, because you can actually always force your hypothesis test to look like this. And that's what you're going to do in practice, because it's a little bit more complicated calculating this. So for example, if you have an alpha of 0.05, let's take this one. Then here you have 1 minus 0.05, which is equal to 0.95. But remember, your tables only give you these alpha levels. So now you'll end up having to use this relationship, which just complicates things unnecessarily. So the trick is to always make sure that you allocate your population 1 and population 2 such that the bigger variance is here and the smaller one is here. So ultimately, even when you do the examples in the book, or in most books actually, you'll find they only do upper tail tests. They're just clever about allocating these population 1 and population 2 so that it's always an upper tailed test. For the two-sided test, the only difference now is you check for larger and small values. So you have now alpha over 2 and 1 minus alpha over 2. And once again, if you make sure that the larger variance is on top in this equation and the small one's at the bottom, then you'll always end up doing like an upper tail test. So you'll end up comparing this one rather than, sorry, I mean this one here, not that one. Sorry about that. So you can have a look at example 10.14 to see how they perform this hypothesis test. So it's just a typical hypothesis test that you should be able to do. On page 799, they give you tables for critical values only. In other words, you'll be able to find this value here given some upper tail, and they only give you specific alpha values. So for example, for let's say one numerator degrees of freedom and one denominator degrees of freedom. So remember the top row is the numerator, and this column is the denominator. So if you go 1, 1, all of these four values correspond to an F distribution with parameter 1, 1. And then that's your alpha level, 0.1, 0.05 up to 0.001. So this little group here is for the F of 1, 1. So let's have a look at now if you want to calculate p-values given this table. So let's look at the numerator degrees of freedom equal to 4 and the denominator degrees of freedom equal to 6. So that means we're going to be focusing on these values, 4, and then this group of values next to the 6. So that's the column of interest. Suppose we had these test statistic values and we're doing an apple tail test. We want to find out what's the p-value. And then we'll also, what if it's a two-tail test? Let's have a look and see how we're going to do that. So what I'm going to do is I'm going to take these values and then put them in a little graph so you can see how it's going to work. So what I have here is a sketch of an F distribution with the different critical values and alphas indicated. So for example, if you look at 21.92, that value was given in that little box of squares that I indicated earlier. And if you go across in that table, so if you have your F tables, have a look. If you go across to the left of that value, you'll find they've given you this alpha level. So in other words, for the critical value 21.92, the area to the right is 0.001. And you can interpret all the other rows in a similar fashion. So you can double check that for yourself. Now, if we've been asked to find a p-value for an upper sided test, then if we are given these critical values I've indicated in blue, then in each case we want to find the area to the right. But none of these values are actually in the table. You won't find them. There's only 4 values. So what you're going to do now, let's start off by looking at the 5.7. We want the area to the right of this value here. So that's all that area. That's your p-value for a test statistic equal to 5.7. But we know that 5.7 is between 4.53 and 9.15. So that means that the p-value can be given as an interval. So just notice 4.53 has an alpha or area right tail probability of 0.05, and then 9.15 has a right tail probability of 0.01. So although 4.53 is on this left side here, the corresponding alpha is bigger than the 9.15 alpha. So that's why when I wrote them, I had to like swap them around so that this makes sense. Okay. And now let's look at the other cases. So what about the 2.16? If you want the area to the right of 2.16, you're not going to find it, but you know that it's less than 3.18. So in other words, okay, if you want the area to the right of 2.16, so everything that side, in other words, I can immediately see that that area is bigger than 0.1. So I'm going to give my p-value as being bigger than 0.1. That's as much as I can say from this. If we look at this case, we want the area to the right of 21.9 or 25.03, and we know that's bigger than 21.92. So if you just compare the probability of getting smaller and smaller as you go to the right, so definitely this p-value is going to be less than 0.001. So if you're asked to find a p-value, this is how you're going to do it, especially if you can't find the value directly in the table. If you could find it directly, like if your test statistic was 9.15, you'd give your p-value as equal to 0.01 because that one's in the table. Now, what if you had a two-sided test? So we want to look at, let's say, for example, an f equal to 5.82. Now, we know that if it was a one-sided test, we know that this p-value is between 4.53 and 9.15. So it's just the 0.01, 0.05 case. You can verify that for yourself. So this is for a one-sided. Now, a simple trick if you want to do a two-sided test now, so I'm going to write it just below, is you're just going to multiply that p-value by 2. So, in other words, your p-value will look like this. So it's going to be 2 times 0.01, so that'll give you 0.02. Everything else remains the same. And this will become 0.1. So if it's a one-sided, you read it directly, and then if it's two-sided, remember to double it. So if you want to get some practice at using the tables and finding p-values, I recommend exercises 60 and 61. Try do them on your own before you look at the memos, just to make sure you're comfortable. So this is your memo for question number 60 and 61. So you can just pause the video at the relevant point. Lastly, let's have a look at how you calculate a confidence interval. So on page 530, you see that they've given you the confidence interval and they give you a bit of guidelines on how to do it. So as we did, as is our custom, when you want to now find the pivotal quantity, you're no longer assuming the H0 is true. So this sigma 1 squared and sigma 2 squared term here, it comes back. They're no longer equal and equal to 1. So you're going to now work from this thing here, which you know has an F distribution with this degrees of freedom. So in order to derive a confidence interval for this ratio, so it's going to be a confidence interval for sigma 1 divided by sigma 2, okay? You naturally need to find something such that the probability of that ratio between those things is equal to 1 minus alpha, and this is going to be your starting point. Um, let's have a look at how you do it. I'm just going to walk you through it, and the next set of notes that we're going to look at now, they are available on ClickUp under the additional notes for this week. In order to derive a confidence interval for sigma 1 squared over sigma 2 squared, we need to start with an expression like this. So we know that our pivotal quantity has an F distribution. So in order to find the different critical values, those ones in particular, it's best to just do a little sketch for yourself. So remember, alpha over 2 is going to be put on either side at each end. But this thing is not symmetric, so this f alpha over 2 is not the same as f1 minus alpha over 2. So you need to put them in separately. So watch out so you don't make that mistake. Now you replace the f with your pivotal quantity, which is just that value there. And then remember, this can be rewritten as follows. So far, everything else remains the same. Okay, but remember, we want to end up with this term in the middle on its own. So that means we need to multiply both sides by s2 squared over s1 squared. So it's the reciprocal of that other part. So this is what you end up with. But remember, we want sigma 1 on top, not sigma 2. So we have to invert everything. And as a result, you'll see that even the signs change. Okay, so be careful not to make any mistakes. And then in this last step now, they've just rewritten everything with the signs now in the usual direction. So that means you need to swap this one, so it comes over here, and then the other one needs to go on the other side. But you'll notice that in the one that I've indicated, they don't exactly look the same. And it's coming from this result that I've indicated over here. So if you remember, f1 minus alpha over 2 with v1 and v2 degrees of freedom is equal to just this term here. So notice here you have 1 minus alpha over 2. Here it becomes alpha over 2. So it's just the remaining probability. And then the degrees of freedom get swapped. So that's where this term comes from. So instead of having that 1 over thing, then you apply the result that I've just given you, and you should get this. So you even see that the degrees of freedom are swapped around, and instead of 1 minus alpha over 2, you have alpha over 2. So this gives you your confidence interval for sigma 1 squared over sigma 2 squared. If you'd been asked to find the confidence interval for the ratio of the standard deviations, then you just take the square root on both sides. So this is the other confidence interval that you might be asked to derive. Example 10.15, you can now have a look at it as self-study. I just want to draw your attention to a small point that they put in there. So if you just look at this confidence interval that they've calculated for sigma 1 over sigma 2, you end up with this. Now, remember, you can use a confidence interval to make a decision for hypothesis tests. So for example, remember equal variances hypothesis test is exactly the same as the equal standard deviations. You do the exact same f-test, and let's rewrite this, and you'll see that it looks like this. We just divided both sides by sigma 1 over sigma 2. So remember, if your null value is in the rejection region, then you do not reject. In this case, the null value is going to be 1. So it's always going to be 1 for equal variances or equal standard deviations. If you look at this confidence interval, 1 is not in the interval. Therefore, it suggests that the two standard deviations differ. So, in conclusion, I'd like you to do exercises 62 and 66 in the textbook and submit your answers on ClickUp. Enjoy the rest of your day. Goodbye.